So now we're going to talk about soil physical properties. I want you to compare and contrast sand, silt, and clay particles and their influence on soil properties. And if I were to give you the percentages of sand, silt, and clay particles in a soil, and I give you access to a soil textural triangle, you would need to identify a soil's textural class. And then I want you to diagram the 6 types of soil structure. Soil texture is defined as the percentage of sand, silt, and clay in a soil. This does not include material that's greater than 2 millimeters in diameter, such as gravel and rocks. So soil texture, again, only includes sand, silt, and clay. This does not include organic material, and texture is a permanent characteristic of soil. As we define soil texture as sand, silt, and clay, sand is the largest of the diameter in particles with 0.05 to 2 millimeter diameter particles. It's single-grained, it has a gritty feel, it's full of silica dioxide. It's what you walk on when you're at the beach. Silt is about 0.002 to 0.05 millimeters in diameter, so it's the next smallest size. It's very smooth, very flowery feel, slightly cohesive. Essentially, this is very weathered sand. What silt feels like is basically wet talc powder, or if you've ever stuck your hand in a tub of margarine, it's basically the same thing. You should probably not stick your hand in a tub of margarine. And the smallest particle that makes up soil texture is clay, which has a diameter that is less than 0.002 millimeters in diameter. Clay is very sticky, it's very cohesive, it's the weathering products of secondary and primary minerals. It's the smallest part of soil texture, and it's what we use to shape, because it has plasticity, into clay pottery. So here's an exaggerated diagram showing the difference in the particle sizes. Sand is obviously the biggest, followed by silt, shown up here in the corner, and then a clay particle in comparison to these, if we magnified it 10 times, would be this size. Clay is teeny tiny. There's a relationship between particle size and the kinds of minerals present. So as we get into the larger structures, sand, it's mostly quartz with some primary silicate minerals. Silt is a hodgepodge between quartz, primary minerals, and secondary minerals, but still a large quantity of quartz. Clay being the tiniest, most of the quartz is weathered out, and we have mostly secondary silicate minerals and a few others. Now, the relationship between particle size and surface area. Contrary to what you may naturally think, smaller blocks will have more surface area than will bigger blocks, because the smaller blocks have all of this internal surface area. So if we took this big block, as you see, there's no access to the inside of this block, so that's a bunch of wasted space. The only surface area is on the outside. All the broken up blocks have all the surface area on the outside and all the surface area on the inside. So ultimately, the smaller the particle, the larger the surface area. Make sure you write that down. That's important. The smaller the particle size, the larger the surface area. As particle size decreases, surface area increases. Make sure you write that down. That's definitely going to be a test question. So as we start thinking about texture and how particle size and surface area play a role, and we know that we have sand, which is large, silt, which is medium-sized, and clay, which is the tiniest, you might start thinking to yourself, well, I guess that means clay has more surface area than sand, and that would be correct. So we start learning the importance of texture after we learn some of those physical properties. Soil texture is important for us to understand because it's going to influence water holding capacity, water movement into and off soil, nutrient holding capacity, resistance to erosion. It will influence crop management, and it will absolutely drive all engineering applications of soil. So when we determine soil texture, we use the field or feel method, which is what you guys did in your very first lab where you learned how to texture soil, or we can use the hydrometer method in lab. So this is a chart that's often useful for learning how to texture by feel. These are examples of ribbons. This ribbon in example A is too thick. This ribbon in example B is also too thick, but this ribbon in example C is just right. So if we're going to use the hydrometer method, we get a cylinder, we fill it with water, a dispersing agent, which is basically a type of soap, and soil, and then we add what's called a hydrometer, and the hydrometer tells us over time the weight of soil still held in suspension. So what we find is that sand falls out first because it's the largest, and then silt falls out second because it's the second largest, and clay stays suspended the longest. So we can take time measurements and figure out the percentage of sand, silt, and clay, knowing that they fall out in that order. We use Stokes' law to figure this out. Now, don't get freaked out by this equation. I'm never going to ask you to apply this equation in class, but I will ask things like, in Stokes' law, what does V represent? In Stokes' law, what does N represent? And ultimately, I will ask you what Stokes' law actually tells us. And what it tells us is that the larger the particle, the faster it falls. So if I were to say, describe to me the purpose of Stokes' law, you would say, the larger the particle, the faster it falls. This is the USDA soil textural triangle. On the left side, it starts from 0 and goes up to 100%, showing the percentage of clay. On the bottom, 0 is on the right, and we move towards the left to find 100%. This is the percentage sand. On the right side, percentage silt starts at the top and increases as we go down to 100%. So, if we were to find the texture of a soil with 20% sand, we would come right here, and 55% silt, we would come in over here. Now remember, 55 is not in this direction, it's in this direction. You would go down. This is a common mistake people make, is you're used to reading graphs going up. So make sure you know that 55 falls between 50 and 60 in this direction. So that would be 55. And then 25% clay, which reads all the way over here. And where they intersect here, where I've drawn a circle, we now know that this is a silt loam. Now there's some examples for you to practice this in your study guide, which you can find linked in week 1, 2, and on the general module page. It shows several percentages that you can type into the United States Department of Agriculture soil textural triangle. All you have to do is Google USDA textural triangle, and it'll bring up where you, the triangle, as well as some percentage boxes. So you can practice on your own and then check your answer. So now we're going to learn about soil structure, which is the way sand, silt, and clay particles are arranged into aggregates or PEDs. You saw some examples of soil texture in week 1. There's 4 general types of soil structure: granular, platy, prism-like, blocky. These aggregates of primary soil separates are basically separated by adjoining planes of weakness. We call these individual units PEDs, or a structural unit. The first structure is granular, which really kind of reminds me of crumbs coming off of a muffin. It's rounded, sphere-like. It generally is found in the A horizon because it forms around the roots of grasses. As organic matter increases, granulation increases, which means this is the best soil shape that you can have. Platy is terrible. It's flat, it's elongated, it makes it very difficult for water to move into soil. We generally find this with fluctuating water tables, freeze-thaw, and machine traffic. Prismatic or prism-like are tall, relatively narrow heads. Now we have two types. We have prismatic, which is what we find in Indiana, and we have columnar, which we find in the salted soils of Utah. You will not find columnar anywhere on this side of the country. You only find it in desert soils where it's dry and there tends to be an accumulation of salts. Columnar has a rounded top to it. Again, you will not find that here, but you will find prismatic. We find prismatic, or any kind of prism, where we see shrink swell causing vertical cracks. Blocky is another subsoil structure that we find. It's roughly shaped like a cube but with some angles. We have two types, angular blocky and subangular blocky. Angular blocky, the edges are sharp enough to kind of poke your finger. I mean, it wouldn't cause you to bleed and it wouldn't be painful, but subangular blocky is a little bit more rounded. We tend to only see angular blocky in really high clay content. This is an image of a massive structure, which is technically structureless. It's a very large clod, at least the size of your fist, that's very difficult for water and roots to move through. We generally see this in sea horizons. Other structureless conditions include single-grained, like beach sand. Massive, again, is mentioned here. So again, you would find granular in surface horizons, like OA. You would find platy really throughout the profile. Prismatic and columnar you can find in B horizons. Structureless single grain and structureless massive you would find in C horizons. The importance of structure helps us to determine drainage of soil or drainage capacity of soils because the structure breaks and creates pores. And the more pores we have, the easier it will be for water to drain through soil. Structure will also influence erosion because if we have poor structure at the surface, it makes it difficult for water to move into the soil. And when water can't move into the soil, it will scour over the surface and cause erosion. Structure also tells us the aeration capacity of the subsoil. Smaller structures make for better aeration. It also influences the ability of soil to be a rooting medium. And again, the smaller the soil structures, the better rooting medium we have. So structure formation is caused by physical forces such as shrink, swell, or freeze thaw, parental material characteristics, clay and organic matter, roots, insects, and fungi.